What I'd like to do now is try and apply the general theory that we've developed to the behavior of torsion bars. So I have a round bar here, and that's the case we're going to consider, and I'm going to apply a torsional load to it. And I'd like to build up a theory similar to what we did for axial bars. And the way that we're going to do this is we're going to try and start by developing a kinematic assumption or observation about the kinematic behavior of the bar under load. And so what I've done here to my bar is I've painted a grid on the outer surface of the bar so we can observe visually what happens when we apply a load to it. So let me go ahead and apply a torque to this by moving the lever arm. When we do that, we can see that there's motion of the system. And the primary motion that you should observe when you look at the bar is that the bar has rotated. And if we look really carefully at the rotation that we see here, we'll notice that the distance between the vertical lines remains the same at any given cross-section. And what that tells us is that each cross-section is rotating as a rigid body. And if we also look at the behavior of the rotations of the cross-sections, we notice that they vary as a position of axial distance from the bottom of the bar. So the cross-sections near the bottom of the bar, they don't rotate as much as the cross-sections at the top of the bar. So we have this observation that the cross-sections rotate, and if we also look carefully, we'll notice that they remain planar, so they don't move out of plane when I've applied this load here. So we have the observation that the cross-sections move as rigid bodies, and the plane sections remain plane. And so out of that observation, we can actually build a nice expression for the kinematics of the behavior of the bar.